Good afternoon, everyone. And today I would like to discuss about dining philosophers problem and how it can be solved using semaphores. Dining philosopher problem is one of the standard problem in operating system. Here there are 5 philosophers P0, P1, P2, P3, P4 seated around the dining table. There are 5 folks F0, F1, F2, F3, F4 beside them. Each philosopher has 2 states, thinking or eat, because the job of the philosopher is to think. And if they are hungry, they will start eating. In order to eat the rice placed at the center of the table, each philosopher have to follow some rules. That is, first he have to pick up the left fork, and then he have to pick the right fork, and he can start eating. If he completes his eating, he has to put back his left fork and then his right fork. In order to do this, each philosopher has to follow this code with entry section take fork I and take fork I plus 1 mod n, where n is the number of forks, and with the critical section, that is eat, and exit section put fork I and put fork I plus 1 modulus n. Now let us see the a normal condition where all philosophers want to eat in a serial manner. That is, first P0 comes and execute the code. According to the code, he lifts fork F0 and F1. And after eating, he will put back the forks F0 and F1, and next P1 enters. And he will pick fork F1 and F2, and after eating he will put back the fork F1 and F2. Then P2 will come and he will pick the forks F2 and F3. And next P3 will come and he will pick the forks F3 and F4. Similarly, P4 will also follow the same. That is, he will pick the fork F4 and F0. There will be no if the philosophers come in serial manner, then there will be no problem of race condition. Now let us see what will be the problem in a race condition situation. Let us say first P0 enters, and he will pick up the fork F0. At the same time, it will be if it is preempted, and if P1 comes and he will pick the fork F1 by executing this take fork I, where I is the index of the uh, philosopher philosopher who is executing this code. Then P0 has to wait till P1 completes his eating and put back the fork F1, so that it will be available, fork F1 will be available to P0. So in order to solve this problem, we use semaphores. Binary semaphores are used to solve this problem. S of I, we use S of I, that is array of semaphores. For P0, he wants 2 semaphores, that is S0 and S1. And for P1, he wants S1 and S2. For P2, he will use S2 and S3. For P3, he will use S3 and S4. For P4, he will use S4 and S0 semaphores. Each philosopher has to wait um, semaphores, 2 semaphores. While waiting, they will put the uh, value of semaphores to 0, and while exiting they will put the semaphores value to back to 1. Initially all the semaphores will be initialized to 1. Now let us say P naught enters and makes the and next he will picks up the semaphore. He will takes uses semaphore 0 and semaphore 1, and next P1 will enter, and when P1 wants to enter at the same time, it will checks for S1 value. Since P0 has entered and may and used the semaphore S1, it is not available to P1. So in currently P1 is blocked. If at the same time P2 will enter the enter this code, the critical section, he wants S2 and S3 semaphores, but S2 and S3 semaphores um, are not used by P0 and P1, so he can easily enter into the critical section. If P4 wants to enter, he can enter with P1 because they are not they are not independent. The independent philosophers can enter into the critical section. Next, let us see the case of deadlock. Let us say first P naught enters by making S naught value from 1 to 0, and at the same time if it has preempted and make if P1 enters and makes the value of S1 from 1 to 0, and again at the same time before lifting the second fork, that is the right fork, let us say S2 has come and he has made the semaphore, P2 has come and made the semaphore 2 as from 1 to 0, then P4 has made the value from 1 to 0 of S3, and S4 also had made the same thing from 1 to 0. Now if P4 has made the value of S4 to 0, if and S0 is not available to him because P0 has made the semaphore 0, S0 to 0. So in this case, deadlock occurs where none of them can enter into the critical section and none of them can eat. So this problem can be solved using the following solutions. First solution, allow only 4 philosophers to be seated in the table. Second, allow a philosopher to pick up the fork only if both are available. Picking must be done in a critical section. Third solution, use an asymmetric solution. An odd numbered philosopher picks up first the left chopstick and then the right chopstick. Even numbered philosopher picks up first the right chopstick and then the left chopstick. Next solution, n minus 1 philosophers will lift the left fork first, then right fork. Nth philosopher will lift the right fork first and then left fork. Now let us see how it will be solved. For let us say for n minus 1 philosophers, they have to follow this code. That is, they have to take first the left fork and then right fork by executing wait s of I, wait take fork s of I plus 1 modulus n. For nth philosopher, they have to execute this code. That is, wait take fork s of I plus 1 modulus n, and wait take fork s of I. That is, they have to take right fork first, then left fork. Let us assume P4 as the nth philosopher, and remaining are n minus 1 philosophers. We have changed here the semaphore values, that is from S4 and S0 to S0 and S4, so that when philosopher P not when they are preempted continuously, when it comes to P4, it first checks the S0 values, which will be taken by P0. So it is not available, it will be blocked. So now P3 so the value of S4 will be 1. So now P3 can easily take the semaphore S4 and it can enter into the critical section. Then after completing P3, P2 can execute, P2 can eat, then P1, then P not. After so there will be no deadlock in this condition. Thank you.